15. Newton's generalized binomial theorem. Let us look at this integral square root 1 minus cosine squared theta integrated over cosine. The lower limit is minus 1 and upper limit is plus 1. And actually, this is in polar coordinates, spherical polar coordinates with the polar angle running from pi to 0. And in this region, sine theta is a positive definite. So this is a sine square theta, square root, that is actually sine. And the differential in here represents a minus sine theta d theta because the lower limit and upper limit is upside down. So if you flip the order, then we obtain this one to be the sine squared theta integrated over theta from 0 to pi. Because 0 to pi, this is the period, single period of sine squared theta. Because sine squared theta is 1/2 1 minus cosine 2 theta. It's a period, it's pi. So this integral exactly vanish, and the final result is half of pi. Actually, Wallace noticed that this integral giving 1/2 of pi is in the middle of these inequalities. Let's see if it is this 1 minus x squared and power is in 1/2, and its power is 0, and then its power is 1. And these two integrals are exactly evaluated using this polynomials integral. This 4/3, and this is exact 2. Therefore, if we consider the power between 0 and 1, so 1/2, power 1/2 is the between the powers 0 and 1, and he noticed that this half of pi is between these two numbers. In addition, using the relation, he guessed the exact value, not exact value, the approximate value that is converging to this exact value arbitrarily closely, and he introduced this infinite product to represent 1/2 of pi, developed from these trivial inequalities. And actually, interpolation, the word interpolation was first used by John Wallis, and this combination of two words, inter and polar, so that each of them represents between and Polish. Young Newton read the book written by John Wallis regarding this approximation method, and eventually Newton developed a generalized way of binomial theorem. We know a plus b to the nth power with the integral power by expanding this, and with the coefficients exactly calculable with the combinatoric factors, that is called the binomial coefficient. But Newton was the first one who was able to expand the power with non-integral powers such as 1/2 or minus 1/2. That is called generalized binomial theorem, and which is well ahead of the actual development discovery of Taylor series by Bruce Taylor. To consider this problem in a rigorous way, we first consider the derivative or integral of composite function. And as a simple composite function, the resultant function is to be the identity function if we make a composite function using a function and its own inverse. And then we exchange the order, apply the inverse function, and apply then again with the function. And the resultant function is identity function that doesn't change anything. Okay, so we have exponential function as a f of x. An inverse function of this is called logarithmic function. Usually we have log and base, and when the base is Euler's number, then we call this one natural log if it is equal to e. So natural log is the inverse function of the exponential function. If we draw a figure, the plot for the exponential function passes that y-intercept is 1. If you make a symmetric plot, so it's x-intercept is 1, and this is y equals x. So if we have such kind of symmetry, then this is a function, and this is an inverse function. And we call this one to be log x, the natural log. It doesn't matter if you write just the log x. The natural one is, in physics, we assume it is its base is natural, the Euler's number. Okay, because this and this are all identity operation, so if we apply the inverse function first and then apply the original function, in here we have f of x is exponential and inverse is a log. So f inverse, that means exponential of log x, is nothing but the identity. As you have noticed, the exponential x is defined for all real number, and log x is defined in the region restricted to the positive x. Okay. All right. In reverse, f inverse is log, and the log with the substitution of exponential is also the identity operation. Next, we consider chain rule. We are so familiar with this, so let me just briefly explain. If we have a composite function, f of g of x, and if we take the derivative with respect to x, then by definition, we take the ratio of the function's difference divided by the argument's difference. And if I substitute the exact definition of the capital F, then we have this form. By the way, this is not a convenient way to compute the derivative of small f. So derivative of small f can be evaluated by dividing this numerator by the difference of the arguments. The difference of argument is this instead of h. So we just move this h in here, and because we intentionally multiplied this, we have to cancel this operation by multiplying this exactly the same factor in the numerator. As a result, the first factor becomes the derivative of small f with respect to g, and the second factor represents the derivative of function g with respect to x. This is called the chain rule. We apply the chain rule to find out the expansion, power series expansion of this 1 plus x to the alpha, where alpha is an arbitrary real number. First of all, we verify this identity. While alpha is an arbitrary real number, and we consider y, that is a positive number, this is y. This is y. Okay, what is the derivative of f? And derivative of f is nothing but the exponential. Exponential's derivative is the same. We can make we can separate the variables. So first replace this one with y as is defined, and y's x derivative is y. Okay, then we move this y to the left hand side and move this one to the right hand side. Then we arrive at a point. The left hand side depends only on y, and the right hand side depends only on x. And this is a trivial total derivative, and we know, everybody knows that this trivial derivative of the total differential can be integrated to find out x. Sure, there should be some arbitrary constant that has been suppressed. Okay, so I don't know how to evaluate this integral. However, keep it as it is, and I know this is trivial x. By the way, by definition, y equals e to the x. Okay, and we know what the inverse function is, so x equals log y. Therefore, I arrive at the point, this x is log of y. So, we have finally obtained indefinite integral of 1 over y. That is log y. All right. I take the derivative with respect to y, both sides, then I can say derivative of log y is derivative of this integral. Derivative of integral is just integrand, everybody knows. All right. Then, if we consider a g of x, that is identical to the exponential function, except that we have rescaling factor alpha to the argument x. So this is exponential alpha x. So this is nothing but this. And why don't we make use of the law of exponents? And alpha can be pulled out as a power, not a power, and it is e to the x to the alpha, and this is f of x. We know what f of x is. F of x is exponential x, and that is also defined by y, so y to the alpha. All right, so f alpha x equals e to the alpha x. And then we know what this inverse function is. So inverse, if I want to know what alpha x is, then I substitute inverse y of alpha. Okay. By the way, inverse function is log, and argument is alpha to the y, and we find that this is this. By the way, what is x? X is log y, so this is alpha log y. As a result, log y to the alpha is alpha log y. We have proved this identity. Next, we consider this one. From this, we derive this. We take the derivative of log of 1 plus x to the alpha. All right. I know this. So let me pull this power alpha out. And this is constant. It has nothing to do with the derivative. So I can pull this alpha out of the derivative. And then we can make use of chain rule We first take the derivative with respect to this one, and then take the derivative of this one with respect to x. This is called the chain rule we just have studied. By the way, what's that? This is a log's derivative. Log's derivative was 1 over something. So it is 1 over something. And we have pulled this out. And what's this? This is trivial derivative. That is 1. As a result, the answer is alpha divided by 1 plus x. Sure, we have assumed that this is 1 plus x is a positive in order this log to be defined. Next, we consider derivative of 1 plus x to the alpha. We recall this, so we can rewrite this one as an exponential log. And the log something alpha power, I can pull this power out. All right. And then we take the derivative after converting into this form. And why don't we take the derivative with respect to the whole thing? Replace this one to be alpha log 1 plus x. Okay, this is the capital X, the exponential capital X, and this is small x, the capital X, and this is itself exponential capital X. And what's that? Derivative of this. So here. By the way, we just have evaluated this derivative, right? This derivative is alpha over 1 plus x. Alpha over 1 plus x. By the way, this is exponential log. What's that? Exponential log 1 plus x to the alpha. What's that? That is just 1 plus x to the alpha, right? As a result, substitute this value for this and divide this 1 plus x in here and have a decreased power by 1. By the way, if I take the derivative of this with respect to x, everybody knows that it is this, but we didn't know whether it is true or not when n is not an integer. Alpha is an arbitrary real number, but we were able to prove that it is true. So we can finally reproduce the Newton's generalized binomial theorem. Okay, let's see if it is true. First, we define the function, this one to be f of x. First of the derivative is alpha with alpha minus 1. We'd like to expand this expression in the vicinity of x equals 0 and in the region in which x, absolute value of x, is less than 1. Does not include plus minus 1 for x. Using this identity, we keep differentiating this expression, then the power by n times, then the power decreases by n, just like the first order derivative is alpha minus 1, nth order derivative has alpha minus n. And when we take the derivative, each time this power is multiplied to the front factor. As a result, alpha minus 1, and if I take the nth order derivative, alpha minus n plus 1 is the last factor. And then I'd like to know the derivative evaluated at x equals 0. In that case, this one vanishes and only the over factor survives. According to the power series expansion that is consistent with the Taylor series expansion that we have obtained in the previous class, we can make a power series expansion of this about x equals 0. Using this derivative rule, I know what the derivatives is for any k. That is, at first time, the leading term evaluated at x equals 0 is nothing but 1. And the first order correction, that is alpha x. The second order correction factor, alpha minus 1, according to this result, alpha minus 1, alpha minus 2. And in addition, we have factorials in the denominator. And this expression does not terminate unless alpha is a positive integer. At some point, if it is a positive integer, this series terminates at alpha equals some n. However, it is impossible to terminate when alpha is, for example, half integer or anything else except for the positive integer. Application of this can be made for the evaluation of this kind of form when x, absolute value of x, is less than 1. Using the formula, binomial expansion formula, we can substitute alpha equals minus 1 half, and here y equals minus x squared. Then we arrived at this kind of form. This one can be used to evaluate pi because this integral is nothing but the arc sine, that is the inverse function of sine. And the expression can also be applied to evaluate the relativistic energy of a massive particle. And again, the trivial substitution of power. This power in here is 1 half, and x squared is y. So we arrive at this point. If I make use of this second term, and this expression becomes 1 plus p squared 2 mc squared, and we can ignore this if p is very small in comparison with the speed of light multiplied by the rest mass if it is very small. If I multiply mc squared both sides, what I obtain is the rest energy plus p squared over 2m. This is the non-relativistic kinetic energy the Newtonian mechanics gives. This is the rest energy of a massive particle that is developed. That is the consequence of Einstein's special theory of relativity. That's it for today. Thank you.